Fork join framework is another important concept in Java. Let's learn about the same. The fork join framework is a concurrency framework which was introduced in Java 7 to simplify the process of parallel programming. It is designed to take advantage of multi-core processors by dividing tasks into smaller subtasks, executing them in parallel and then combining their results together. The fork join is very similar to executor service, which we learnt about earlier. In the interest of refreshing your memory, executor service mainly consists of some sort of data structure which stores the tasks to be executed, and there is a pool of threads which pick the tasks from this data structure and work on the task. Depending on the use case, you could just execute a task and not return anything, or you could return a value from the execution of the task. So in these two aspects, the fork join framework is exactly the same as the executor service. However, there are certain dissimilarities between the executor service and fork join framework. The fork join is different from the executor service in the aspects of subtask creation, and the fork join framework can create subtasks, which is not the case with the executor service. Now let's learn about the differences between the fork join framework and the executor service. The fork join framework differs from the executor service in two aspects. The first one is the task producing subtask, and the second one is per thread queuing and work stealing. In the case of fork join framework, a task is capable of creating subtasks to simplify the problem being solved. Consider this as the standard divide and conquer approach, which is not the case with the executor service. Unlike the executor service, where there is a shared task queue, the threads in the fork join framework have their dedicated task queue. There is also this mechanism of load balancing where a thread could pick tasks from the other queue. This approach is called as work stealing. Now it's time to learn why do we have fork join framework. You may be wondering, why do we have yet another framework on top of all the things that we have learnt so far in the multithreading? Well, fork join framework is not there without any reasons. Below are a few reasons why the fork join framework was provided as part of the Java. The first one is the utilization of multi-core processors. Modern processors have multiple cores, and traditional single-threaded or poorly managed multi-threaded applications do not fully utilize the computational power of these processors. The fork join mechanism efficiently manages multiple threads to leverage all the available CPU cores. The next one is simplified parallelism. Writing parallel code manually is a complex and error-prone activity. The fork join mechanism abstracts out much of this complexity, and it makes it easier to develop parallel applications. Finally, on the list of why do we need fork join framework, we have this concept of efficient work stealing algorithm. The framework uses a work stealing algorithm where idle worker threads steal tasks from the busy threads. This ensures that all the threads remain productive and improve the overall performance. So, as I told earlier that we have queues on per thread basis, and let's say a thread is done with its execution of the tasks in its queue, so in that case that thread could steal work from the other threads or from the other queue where it has some other tasks aligned to be executed. It's very equivalent to the mechanism of load balancing. So you see, the fork join framework has a certain pattern to it, and due to this, we have certain use cases which fit very well with the uses of this framework. For example, sorting a large data set, performing operations on large matrices, processing large collections of data in a parallel fashion, and so on and so forth. Now it's time to learn about the key concepts in the fork join framework. Forking in the fork join framework is the process of breaking down large tasks into smaller independent subtasks which can be executed concurrently. This is achieved using the fork method provided by the fork join task class. The next concept is that of joining. What it refers to is the process of waiting for the completion of a fork task and combining its results. This is done using the join method. Then we have the recursive task. The recursive task is an abstract class and it is used for the task which return a result. It is parameterized which means that the type is the type of the result which is produced and returned by the task. So whenever there is a need to compute a result and return it after completing the task, the recursive task class should be used. Loosely speaking, you could imagine this to be parallel to the callable interface. Then on the list, we have recursive action. It is used for tasks which don't return any result. It does not accept any types. When the task performs an operation which does not need to return a value or a result, we should use recursive action. And loosely speaking, you could imagine this to be parallel to a runnable interface. So what is a fork join pool? Let's learn about the fork join pool, and I promise that this is going to be the last theoretical topic in this section before we move to the more juicy implementational side of fork join framework. Well, fork join pool in Java is a specialized implementation of the executor service interface, and it is designed so to support the fork join framework. It is optimized for parallel processing and efficient management of tasks, which can be broken down into smaller subtasks. Below are some key concepts and aspects which are related to the fork join pool. We have this concept of work stealing algorithm. So fork join pool uses a work stealing algorithm to efficiently manage and balance the workload among threads. When a thread finishes its task, it can steal tasks from the work queues of the other threads, ensuring that all threads remain productive, and it reduces the idle time as well. Next, we have parallelism. So the pool can automatically determine the level of parallelism based on the number of available processors. You can also specify the level of parallelism when creating the fork join pool instance. So we have two operations like fork and join. So the tasks submitted to the fork join pool can be split into smaller subtasks, and their results can be combined together. This mechanism supports the divide and conquer approach for solving the complex problems. Finally, the fork join pool is designed to manage the instances of the fork join task and its subclasses, which are recursive task and recursive action. So these tasks encapsulate the logic for splitting the work and combining the results. So in nutshell, to summarize the theoretical section, what we have is a fork join framework, and fork join pool is the implementation of it. So essentially, fork join pool is a special implementational case of the executor service where the focus is around the parallelism, and it does so by utilizing two concepts. First is fork, other is join. So fork is basically creating the subtasks, creating the subchildren of a particular task, and join is like collecting the results from the forked subtasks. So essentially what we are doing using the fork join framework is dividing the tasks into subtasks and then asking the different threads to work on these subtasks in parallel, and finally the result is collected and the final outcome is given back to the caller. So in a way, it's a parallel implementation, it's a parallelized implementation of the divide and conquer strategy. So now let's move forward, and now that we have learned most of the basic concepts related to the fork join framework, we shall start with some code implementation for these concepts. So I will start by creating this package. Let's call this package as fork join. And as I mentioned earlier that we have two classes. One is the recursive task, other is the recursive action. So this particular demonstration would be for the recursive task. In the next one, we will see how we can make use of the recursive action. So what I'm planning to implement is a code wherein I would like to search for occurrence of a given number into an integer array. So let's start with the implementation. So let's create this class and let's call this as search occurrence task. This is going to extend the recursive task, and this is going to return integer. So basically integer is the type which it accepts. So if you see the implementation, it's going to extend the fork join task, and the fork join task is going to implement future. So now going back to the code, it's giving certain error. So the idea is that it's enforcing to implement certain unimplemented methods. So let's do that. And the method that we need to implement is called as compute. And by the virtue of the type that we provide, which is the integer, it's going to return integer from this compute method. Alright, so this particular class will have a few things. For example, first is it will have an integer array called as ARR, then it will have a start index, then it will have an end index, and it will have a value which is called as search element. So let's create the constructor for this class, and we are going to initialize all these values. So to begin with, we just have this compute method. So let's say I am going to provide a private method which is going to search for the occurrence in this particular array for a given element. So let's call that method as search, and let's implement it, and probably we will return the value. So private integer search, and let's have the value as 0 to begin with. And what we will do is we will start from the start index, then it will go till the end index, and we increment the index value. If the value at index I happens to be the search element, then we increment the count. And finally, when we are done iterating over the array, we are going to return the count value. So this is the search method. So please note that as of now we are not making use of any fork join concepts. So we will introduce the fork join concepts in a while, but for now let's complete the implementation. So this is about this class, and let's have the runner class wherein we will be invoking this particular compute method somehow, that we will see in a moment, using a main method. So let's create a class, and let's call this as fork join pool demo, and we have a main method. So we will have an array, let's say the value is up to 100, and we will have a random variable. Why we are going to need it, we will come to see it in a moment. And we populate this array with certain random values. So for each and every array index, we are going to provide certain value, and that would be random dot next int. So that is 10 plus 1. So essentially I am going to populate each index in the array with a value ranging from 1 to 10. And we have a search element which is again a random value, so random dot next int, then we have 10 plus 1. And what we are going to do is we are going to create a fork join pool. So new fork join pool, and remember that I told in the theory section that if you don't provide the number of processors, it will by default figure out how much parallelism is required. But in this case, let's provide the number of processors as well. So runtime dot get runtime dot available processors, and it's complaining that we should close this resource. So probably we can go ahead with try with resources. Alright, now what we need to do is we need to make use of the fork join pool. And the way to do this is we need to create an instance of this task which has extended this recursive task. So let's do that. Let's create an instance of this task which is search occurrence task, and let's call this as task new search occurrence task. Let's pass the values, which is the array. Start would be 0, end would be array dot length -1. These are the indices of the array, then the search element, and we are going to call pull dot invoke, and here we will pass the fork join task, and let's capture this as the value of occurrence. All right, so let's print the value that the array is dot to string arr, and finally system out println %d found %d times, then search element and occurrence, and it should be printf, not println. So let's correct this, and now let's run this code and see its output. So please note that we have not made use of any fork join pool concept as of now. We will do so in a moment. So let's run this, and we can see that the value 9 has been found 6 times. So you could go ahead, implement this code, or probably copy the code from the GitHub link that will be shared in this video, and you could try to execute this, and from this particular value you could validate it. So it's working fine. I have validated it. Now what we will do is we will try to introduce the fork and join concepts. So in order to do so, what we do is we go to the compute method, and we first of all compute the size of the array, which is int minus start plus 1. And if the size happens to be greater than 50, then we are going to do some operations. Otherwise, I am just going to call the vanilla search method, which is return this search method that we were using anyway. So when the size happens to be greater than 50, we will divide this task in two halves, and the way to do this is find the middle index, since start plus end divided by 2. And in order to create the fork of the task, we will have to first create the task objects. So what we do is we can create the task object, which is search occurrence task. Let's call this as task 1, then new search occurrence task, pass the value. The start value is the start index, the end value becomes the mid, and then we have the search element. Next we create the other task, which is task 2, and then we call search occurrence task. Then we have array, and the start value becomes the mid plus 1, and then the end value becomes the end, and then we have the search element. So if you are familiar with the concept of binary search or any divide and conquer algorithm implementation, you would find it very similar. So essentially what we are doing is, let's say there is an array with some values, right? Something like this. So what we are doing is we have to do some processing, some operation on this array. So essentially what we are saying is that, all right, let's say if I have these many values, which is let's say 6 values. So I don't want to do operations on the entire array. Rather, what I want to do is I want to split it. So if I were to search this array for all the 6 elements, it will take some time. What if I wanted to search for some value on this particular array itself? It will take less time, right? Because we are doing the search operation on a smaller sized array. So that is the whole concept, where we are finding the mid value, which is let's say somewhere here, and from here to here, this is my first section of the array in which I need to do the search, and this is the second section of the array in which I need to do the search. And this needs to be done till the time this threshold is not met. So for example, let's say this array is somewhat of let's say bigger size, maybe 100 or 200. Then in that case, first split would be 100-100, second split would be 50-50, and when the size is less than 50, then in that case it will come to this section and it will say, all right, the size is less than 50, the size is less than the threshold. Then in that case we can go ahead and do the normal search. But till the time size is greater than the threshold, that is 50 in this case, it will go and break the task into smaller tasks, and that is where we have made use of this task. So the next process in this implementation would be to call fork method on these tasks. So task1.fork, then task2.fork. So what happens is that this task.fork is going to create another subtask. So if you click on fork, you can see that it is going to return the fork join task itself, which is basically this recursive task or whatever implementation you have here. Since this class is implementing recursive task, then this particular fork will also return this recursive task, which is the search occurrence task, but for a lesser search space, right? So if that is clear, let's move ahead and understand how we can fetch the value from these subtasks that we have created. And the way to do that is by calling the join operation. So in a way, you could try to correlate this with the way in which the recursion works, right? And it is pretty much evident by the name as well. So basically it's nothing but a kind of recursive call in a multi-threaded context, wherein you have created different subtasks, and all those smaller subtasks could be picked up by different threads and could be executed in parallel. So it's nothing but some sort of recursion on steroids due to reason that we are making use of parallelism and multithreading and all those concepts, which are going to give us some boost with respect to the performance. So now let's move and see how we can collect the value. So the way to collect the value out of a task is by calling dot join method. So let's say task1 dot join. If you try to capture it, it will be some integer. Why integer? Because that is the parameter that we have provided here. So you could do this way, or probably we could just simplify it by returning task1 dot join plus task2 dot join, and that's the whole implementation. So now let's run this code and see the output. After executing this code, I will give you another walkthrough so things will be much more clearer. So see, this value has been found this many times. So basically 10 has been found these many times. So basically what we have done here is that we have implemented one of the implementations of the task, which is this recursive task, and one of the implementations of the fork join task. And we have certain data structure on which this task is going to be performed, and the data structure of the choice here is an integer array, and our use case is to find how many times a given value is going to be repeated or is going to occur in the given array, and that is the search part of it, and that is what we had in the beginning. Then what we did is we started with the implementation for the compute, and in the compute we first found out what is the current size of the array on which we are performing this operation, and we had a check that if the size happens to be less than 50, then we are simply going to make use of this search method, and if that is not the case, then we are going to break this larger task into smaller tasks, smaller subtasks. And the way to break this is find the middle point in the array, the middle index in the array, and then create two tasks out of it, wherein we have the array itself, then we have a start, then we have a mid value and the element that we need to find. And in the second task, we are going to have the same array, and the search space is provided from the mid plus 1 as the start value and end as the end value. And search element is anyway the element that we need to find. And after we have created this template for these two tasks, we are going to call fork on these two tasks. And when a fork is called, what essentially happens behind the scene is this thing is called recursively with this particular search space, this particular search space. So the search space is going to reduce, it's going to get smaller and smaller, and likewise when this fork is called, similar thing is going to happen. And finally this will keep on happening till the time we have the size, the search space, greater than 50. And after some time the recursion will reach its base case, and then we will like to retrieve the value from that recursive task that we have executed. And the way to do so is by calling dot join. There are some other methods as well, but in this example we are going to stick with dot join. So let's say task 1 has accumulated certain value and task 2 has accumulated certain value. So both the values will be added, because consider this as a binary tree where we are making calls in two directions, in the left side and in the right side. And once you are done with the traversal at every point of time from every node, you are going to get some value. So that is what the intent is, and that is the way to visualize this code. So that is how we are going to make use of the recursive task to implement fork join framework and do this operation. So before we move to the next implementation, which is for the recursive action, I would like to give you a small homework, and what you could try is you could try to implement this for the use case where we wish to find out the summation of all the elements in a given array. So it would be something similar to this, but I think you should try it out on your own, and it would really help you in cementing the concepts related to the recursive tasks. So now let's move to the implementation of the other thing, which is the recursive action. So let's create another class, and let's call this as workload splitter. And what I'm trying to build here is that there is a class and it has some workload, and based on certain workload it's going to either do its operation on its own, or else it's going to split the workload, or the task rather, into two halves. So this is what we are going to implement. So let's start with the implementation, and this workload splitter class is going to extend recursive action. And as I told earlier in the theory section, that this recursive action is not going to accept or expect any sort of parameter, and neither does it return anything. So let's implement the unimplemented methods, and again the unimplemented method is compute. The only difference is that since it does not return anything, we have a void over here. There is nothing to return, right? So let's have a value and maybe call this as a workload. Let's have a constructor initialize this value, and in the workload what we are going to do is we are going to inspect the value of workload. If the value happens to be greater than 16, then we are going to do certain things. Otherwise, this particular task is going to be implemented without any splitting. So let's print some message. We are not going to have any fancy implementation as such. Rather, we are just going to print certain messages to explain the concept. So workload within limits, task being executed for workload, and then the workload value. And what happens when the workload is greater than 16? Well, first start by printing some message. Workload too big, thus splitting. And then the workload is given in the message. So first of all, we find the first workload, and this is going to be workload divided by 2. Then we find the second workload, and this is going to be workload minus first workload, right? So again, very similar to the recursive task that we had in the previous section, in the previous example rather, we will create two tasks here for the workload splitter. So maybe call this as first split, then workload splitter, pass the first workload value, and then workload splitter second split. Then call workload splitter, provide the second workload, and we can call first split dot fork, then second split dot fork. Alright, and that's it. Since we are not intending to extract some value, and that is the reason we have made use of the recursive action, so we are not going to call any sort of join or any value that we need to fetch out of this. So that is all with respect to the implementation. Here we are just making certain load balancing kind of mechanism, wherein if needed, if the workload is too high, then in that case we are going to fork two new tasks, and those tasks will be working on that workload. So let's say to begin with, if the value is 64, then the value is certainly greater than 16. Then the workload will be divided as 32, 32. So the first load is 32, second load is 32 again, and again this value is greater than 16. So again the load will be divided into 2. So the first load becomes 16, second load becomes 16, and since that is the value, we don't need to go inside this thing. Rather, we will come to this thing and we will do the execution on its own. So as I told earlier that there is no any execution as such, rather it is just going to mimic certain behavior around the workload by making use of this recursive action. So now let's demonstrate this implementation and write the code for the same. So let's create a class. Let's call this as workload split demo. Let's have the main method, and we will create the fork join pool. So let's call this as pool and new fork join pool. Again, let's pass the available course, and again this will complain regarding an open resource. So we can resolve this by putting inside the try with resources block. And the way to use this is create an object for the recursive action class that we have created, which is the workload splitter. So let's call it as a splitter, then workload splitter, pass the value as 128, then call pool dot invoke, and let's pass the splitter object, and that's it. So this is what we have implemented. Let's execute this task. Let's execute this code and see the output. So here is what we have. To begin with, workload too big, this is splitting. Workload too big, this is splitting, and so on and so forth. So 128 got split into two halves, 64 and 64. 32 got split into two halves. 64 rather got split into two halves, 32 and 32. And so basically 32 and 32, and this one is 32 and 32. So as I told earlier that these things are executed, all these tasks are executed by threads in parallel. So based on the thread scheduling, you are seeing that we are having some sort of not in sync kind of response, but the idea is that the number is getting split into two halves. So 64, 64, each 64 is getting split into two halves, right? One half here, other half here, and further the 32 is getting split into 16. And since 16 happens to be well within the reasonable limits for the workload, we have this message that workload within the limits, task being executed for the given workload. So these are the messages that we are seeing. So that's it about the implementation of the recursive action, and that is the way in which you could implement it. So that should be it for this particular topic of fork join in Java.